Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called Smart Grids, Buildings Optimization. Lecture prepared by Engineer Jesus Velasquez Bermudez, Ph.D. In 2014, IBM estimated that companies in the energy and utilities sector, which used big data and analytics, reported 23 times higher productivity than those that did not. EI, Internet of Energy. Energy Internet, the Future Electricity System, Overview, Concept, Model Structure, and Mechanism. The Internet of Energy, A, is a futuristic evolution of the electrical system, conceptualized as an energy exchange network. Its features, such as the plug-and-play mechanism, the real-time bidirectional flow of energy, information and money, can bring significant benefits and innovation in the production and utilization of electricity. A integrates small-scale renewable energy systems, electrical loads, storage devices, and electric vehicles for an efficient energy transaction supported by emerging technologies such as the Internet of Things, vehicle grid, and blockchain. Currently, in 2020, there is no expanded A-work model. The literature is scarce, which makes research in this area significant, novel and timely. The figure shows energy internet across the globe. EI, Internet of Energy. The Smart Grid, GS, is an innovation with the potential to improve the electricity grid during the 21st century. Due to its distributed generation, universal control, two-way digital communication, and self-monitoring functions, SG has acquired considerable appeal. Using contemporary information and communication technology, the SG can regulate the production, distribution, and transmission of energy, and develop intelligent monitoring systems. In addition, the SG can manage the energy market, control decentralized energy resources and rebuild infrastructure, improve grid efficiency, reduce generation cost, possibly reduce load pressure, improve system reliability and sustainability, and maximize system capacity without modifying its physical infrastructure. SG and DSM enable a new era. Their simultaneous onboarding can facilitate citizens' transition to smart, sustainable, and affordable communities. Since SGs can be networked or operate on islands, and that the Internet of Things, IoT, is a technique for connecting people and things, anywhere and anytime, with anyone and anything, through any electrical network or service, SGs serve as the fundamental pillars of A. So with the installation of smart meters in residential areas, it is possible to monitor energy consumption in real time. Therefore, A is considered a general application of IoT for the energy sector. A is made up of a variety of components and techniques, which can be divided into three classes: communication systems, control algorithms, and power systems. Electricity generators and users, known as prosumers, are interconnected with renewable energy resources, RERs, electrical loads and storage systems, opening endless opportunities for energy sharing. A is a breakthrough innovation because it facilitates two-way flows of electricity and data in real time. An energy cell can house local generation facilities, electrical loads, storage devices, and electric vehicles, individual residential consumers, small-scale commercial/industrial consumers, or groups of these entities are also defined as energy cells. Tens of hundreds of these power cells are connected to the E to exchange energy, sell surplus energy for profit, or buy substandard power. The physical connection on E is operated and maintained by the utility cells. Being a separate entity, the utility cell provides ancillary services to maintain the stability of the electric system. The clearinghouse collects all the information about demand, supply and forecasts, and performs market settlement algorithms to schedule the optimal dispatch and determine the market settlement price. The development of the Internet of Energy, A, as a network of energy intranets, is a decentralized form of technology adoption, which is expected to be faster than conventional centralized technology development projects. The design and development of easily deployable devices do-it-yourself, DIY, oriented to the A will result in faster decentralized expansion, for example, solar PV modules with integrated inverter. Demand-side management. Higher consumption demand can cause the load factor deteriorate, average load divided by the peak value, making the system unstable. This can be fixed by rescheduling the distribution system's peak load periods using the proper objective and DSM methodology. The load profile curve can be altered using 6 DSM techniques. Demand-side management techniques. Smart meters indicate when and how to use energy, and they can change consumption habits based on grid pricing patterns. Based on the data collected from the customer, the company calculates and provides a pricing pattern, like time of use, TOE, which is used for load planning. A switchboard plays a crucial role in any power grid. It is used to separate shiftable appliances from non-shiftable ones. The Smart Planner, SS, is responsible for scheduling and decision-making about appliances. Optimal performance is achieved by combining SS and the appliances. The main power contactor functions as a power circuit breaker to transmit electrical signals from the power company, or from the microgrid, MG, or SG resources to the appliances, with the help of low-power devices and the distribution board. Thanks to the smart meter, the adoption of A allows the user to monitor energy costs and consumption peaks in real time through the ThingSpeak platform. For purposes of residential load management, the home appliances are divided into two categories. The first consists of shiftable loads, such as vacuum cleaners, washing machines, etc., that can freely be shifted to operate at different times of day without negatively impacting customer convenience. The second type is non-shiftable loads such as electric vehicles, air conditioners, and water pumps, which cannot be operated in different time slots. The table shows the rated information of both shiftable and non-shiftable residential loads. There are 3 water heaters, 8 air conditioners, 4 electric vehicles, and 2 water pumps. All other appliances have only 1 unit. The table shows the detailed operating hours and energy consumption of each appliance. A flow chart illustrating the smart DSM strategy is shown in the next figure, whose steps are: the first step is to conduct a survey to gather load data. A load profile is created from categorized loads, which includes both the shiftable and non-shiftable appliances. The load curve is used to establish the durations of peak and off-peak periods. The amount of energy used in an hour is compared to the maximum allowed for that period. The load shifting reduces excessive energy consumption by redistributing it among various appliances in use at a given time. It is utilized if the system has shiftable loads. Once the process is complete, a period of 2 days is dedicated to supervising the entire process. Loads can be covered by network or SG resources. If the energy consumption is less than the total energy of the RERs, these RERs are used to power the loads. Otherwise, the electricity grid compensates for the energy deficit. Optimization model for demand-side management. With the idea of obtaining optimal solutions, a cost-effective optimization model is used for the programming of residential appliances, which seeks to optimize the operating period of the appliances through the load displacement technique. The energy generated by SG renewable energy resources, RER, is considered together with the energy generated by the regional electricity grid. This model simulates TOE pricing. The results show that the model is effective in scheduling the electrical appliances in a residence, which benefits consumers by significantly lowering their electricity bills. The MIP model. The appliance model operations are a set of sequential phases of uninterruptible power, each of which uses a given total amount of electrical energy. For example, the typical phases of a washing machine are pre-washing, washing, rinsing, and spinning. The set of phases is also called the power profile of the appliance. Depending on the appliance, the duration of the phase may vary, as long as the delay between phases. For example, the spin of the washing machine should begin within 10 minutes of finishing rinsing. The total energy given for a phase may be evenly distributed over time, or it may vary. The MIP model represents the latter case with per phase limits on instantaneous energy consumption and includes three classes of energy sources: power grid, domestic renewable energy, and energy storages. The power grid announces the maximum amount of energy available, the maximum power, for each instant. This maximum power may be different from the actual maximum power of the user's contract. In fact, a common feature in the smart grid paradigm is that maximum power is broadcasted dynamically according to the state of the grid, so that users adjust their demands and thus prevent dangerous power outages. Along with maximum power, the cost of energy also changes over time. Renewable energy sources could provide free energy, but with limited availability. For example, the performance of a PV plant depends on geographical position, weather conditions, and weather. The smart grid makes it possible to store energy when the price is low and use it more when the price of energy is higher. This feature represents a significant degree of freedom in terms of optimization. The proposed load shifting based DSM schedules shiftable loads so that the energy consumption curve is as close to optimal as possible. Additionally, time slots and movable loads are treated as variable components. The goal is to minimize the user's electricity bill, in addition to lowering the peak energy consumption to improve the grid's efficiency. The constraints that are considered during the load planning process are related to demand-side management techniques. For example, the total number of shiftable loads must exceed the total number of shifted hourly loads. Otherwise, the inflated demand must be contained. In addition, mobile loads have a displace time limit, which can be brought forward or delayed within an allowed range. There must be more displaced appliances than mobile devices in step T. The load demand for scheduled loads throughout the day should be equal to the daily demand consumption for loads before scheduling. The figure illustrates the TOW pricing pattern that was been adopted. The figures are: orange, A, non-shiftable load profile on an hourly basis based on the load data. Black, B, hourly curve of shiftable loads is presented, and blue, C, depicts the total load profile, which includes both shiftable and non-shiftable loads. As the time intervals, horizontal axis, shift, the magnitude of energy consumption is also altered, as peak consumption is shortened and peak to average energy is reduced. It is assumed that the adopted virtual load data is approximately actual simulated household load statistics on residential structures. 4 cases of operation of microgrids, MG, and electricity grids are analyzed below. The figure illustrates the amount of energy generated by the microgrid, MG, and the grid, the amount of energy consumed by loads, and the costs associated with the grid. It is assumed that the supply power of the MG is set to 0% of the total energy consumed, so it is not MG power, which means that the cost will be high. It is assumed that the supply power of the MG is set at 50% of the total energy, so there is a deficit in the electricity supply that will be covered by the electricity grid, and the cost will be high. It is assumed that the supply power of the MG is set to 100% of the total energy. There is no shortage of power supply because the power of the MG is equal to the electrical consumption. Consequently, the total energy demand is covered by the GM resources. There are no costs in this case because all loads are supplied only by GM resources. It is assumed that the supply power of the MG is set to 125% of the total energy. No power is purchased, but power is sold from the adopted MG to the utility grid, as the MG power has been expanded by 25% of the total consumption. The cost curve is the inverse of the first case. 3 meta-heuristic algorithms were used to generate the optimal schedule. Binary Orientation Search Algorithm, BOSA. Cockroach Swarm Optimization, CSO, and Sparrow Search Algorithm, SSA. The figure shows unscheduled and scheduled loads using A, BOSA, B, SSA, and C, CSO. In all cases, residential users can significantly reduce their daily electricity bill by optimal scheduling loads. Peak demand, electricity cost, computation time, and robustness tests are compared with the genetic algorithm, GA, another meta-heuristic. The figure shows A. Maximum energy consumption and B. Electrical costs, for both programmed and non-programmed load profiles. Figure demonstrates the peak energy consumption and total electricity cost for both unscheduled and scheduled load profiles. The maximum unscheduled energy consumption and cost are shown as 114.2 kilowatt hours and $650.50, according to the black bars. With the proposed DSM, peak consumption energy is reduced to around 87 kilowatt hours by all algorithms, except for the BSOA, red bar, which can produce peak consumption of up to 85.8 kilowatt hours. The scheduled electricity costs are reduced to 5,438 cents of USD. The results indicate that the optimal DSM can properly address the shiftable load in the presence or absence of A. The figure shows the convergence curves for BOSA, SSA, CSO, and GA. The figure demonstrates the mean of peak demand and the standard deviation for a total of 20 runs. Being metaheuristics, runs do not always give the same results. The mean value of the CSO is the lowest in comparison with the other algorithms. The results is 86.61 using CSO with DSM and 114.2 without DSM. The BOSA algorithm has the smallest deviation, so it is considered superior to the others. It results in peak demand of 85.8 kilowatt hours, a cost of 5,438.98 cents of USD, and 16.3% savings. HEM, Home Energy Management Systems. A survey of home energy management systems in future smart grid communications is a seminal research paper originally published in 2013. The paper offers a systematic review of home energy management, HEM, schemes, underlining their fundamental role on the consumption side of the smart grid. The main goal is to make electricity consumption smarter and more efficient through the systematic coordination of appliances and local resources. The main benefit is reduced electric bills, decreased peak demand, and decreased peak average ratio, PAR. Various pricing schemes should be considered, such as real-time pricing, RTP, hour of use, TOW, tilted block rates, IBR, and maximum critical valuation, CPP. The management strategy categorizes HEM schemes into two types, communication-based and optimization-based. Energy management or home energy management, HEM, is a term that has been applied with different meanings in different situations. It is a broader term, but our concern is energy savings in companies, public organizations, governments, and households. In 2013, 40% of global energy consumption occurred in residential buildings. In the case of the smart grid, consumers can generate domestic energy from distributive generation units. The overall architecture of HEM comprises the following components. Sensing and measuring devices are used to measure physical quantities, such as temperature, humidity, or light, or to detect movement or room occupancy, to name a few. Smart meters are commonly used by HEMs, collecting the detailed energy consumption of individual appliances and other information related to human activities. Smart meters also facilitate two-way communication between HEMs and the utility. Smart appliances consist of typical household devices, such as dishwashers, refrigerators, or air conditioning units, with computing and communication capabilities. Power generation devices such as photovoltaic, PV, panels and wind turbines are also considered. Smart appliances communicate with a central platform, which manages data and coordinates appliance uses. User interface, a device through which residents interact with the HEM. The device can be dedicated or for general use, such as a computer terminal with touch screens, and even mobile applications on iPhones. Central platform aims at managing and optimizing energy usage. It receives smart meter information and adopts a scheduling mechanism, usually computed via an optimization approach, assuming a given performance index. Energy bill is a common choice, along with comfort, peak reduction and GHG. ORM, a linear programming, LP, model, minimizes the cost of electricity at home. The model assumes that a day is divided into consecutive time slots of equal duration with different electricity prices, such as the tow tariff. The objective function ensures that the model reduces the home's energy costs by organizing appliances at the right times. The input for the ORM model is the consumer requests and then provides the optimal programming of the device's output. In-home energy management, IHEM, is a scheme for home energy management. The scheme uses smart appliances, a central energy management unit, EMU, and wireless sensor home area networks, WSANs, for communication among the appliances, the EMU and smart meters. IHEM uses Zigbee protocol for the implementation of wireless sensor network, organized in cluster tree topology. The application is based on Appliance Coordination System, ACS. Unlike ORM, consumer demands are processed in near real time in IHEM. In the absence of optimization models, by employing IHEM, the maximum load can be reduced by up to 5%. IHEM also reduces carbon emissions and energy consumption costs. For appliance-to-device communication purposes, IHEM uses smart appliances, a central energy management unit, EMU, smart meters, and wireless home area sensor networks, WSANs. IHEM uses the Zigbee protocol for the deployment of wireless sensor networks, organized in cluster tree topology. The application is based on Appliance Coordination System, ACS. Figure shows the flow of messages in an IHEM application. The Accord scheme has been proposed to benefit from tow pricing and reduce energy costs. The objective of Accord is to transfer consumer consumption to periods of lower demand. Domestic WSNs are used for the delivery of consumer requests to electric units. The rate of consumer requests has a considerable effect on reducing energy costs. Energy consumption decreases significantly with an increase in consumer application fees. On the other hand, the participation of consumers in the energy management program improves the efficiency of the system. This scheme only considers the scheduling of home appliances. The Optimal and Automatic Residential Energy Consumption Scheduler, ECS, model is a linear programming problem, for real-time prices that needs a price predictor. The combination of the price predictor and the ECS significantly reduces the peak-to-average ratio, PAR, in the load demand for different scenarios. The math formulation is in the image. The possibility of multiple pricing schemes comes with the need for HEM programs. With local generation, feed-in, that offer greater savings compared to those without feed-in. Below are several schemes of HEMs. The figure shows the savings for both electrical and non-electrical systems. The simulation results show the reduction in PAR by solving the optimization problem by LP techniques. The results are satisfactory for utilities. Accord-Fi is another energy management scheme for energy smart homes. At Accord-Fi, both appliances and distributed energy resources are programmed with the aim of reducing energy bills and greenhouse gas emissions. Accord-Fi schedules consumer requests considering peak hours, local energy generated and other conflicting requests. Accord-Fi uses WSNs for communication between EMU, appliances and smart meters. OLM is a residential load management strategy based on optimization. The OLM requires several interests, the forecasting and planning of activities by the users, to form an objective function. For example, several interests are local power production, such as solar and wind, load, and electricity prices for next day. OLM can be linear or nonlinear and can be solved by mathematical programming or by heuristics. Simulation results show that OLM can reduce energy bill by 8 to 22%. The Decision Support Tool, DST, has as its main objective to help users make intelligent decisions during the operation of their device. A HEM program can be augmented by adopting DARE coordination in parallel with apparatus coordination. The coordination value has been calculated first for the case where each DARE is programmed independently and then for the case where the DARE cooperates with each other. DST is composed of DARE scheduling algorithm and an energy service model. The net benefit of the consumer is maximized by scheduling the controllable DARE according to the scheduling algorithm, and the consumer energy bill is reduced by between 16 to 25%. The figure shows a DST smart home case. The table summarizes several HEM schemas. On a conclusion note, In this work we have revisited the need for home energy management for efficient usage of electricity and smart grid. Efficient electricity consumption is fruitful in reducing peak load, reducing electricity bills and minimizing GHG emissions. The smart grid is facilitated by two-way communication and effective home automation, so a smart home can be designed through optimization, which produces the largest profit in bill reduction. The figure shows the vision of the HEM system architecture, in 2013, for the smart grid of the future. Optimal smart home scheduling. The term smart grid refers to an electricity transmission and distribution system that incorporates elements of traditional and cutting-edge power engineering, sophisticated sensing and monitoring technology, information technology, and communications to provide better grid performance and to support a wide array of additional services to consumers. A smart grid is not defined by what technologies it incorporates, but rather by what it can do. The key attributes of the 21st century grid include the following. The figure shows an example of a smart grid. The architecture of a smart grid includes critical elements. Smart meters, they allow you to measure consumption in real time and communicate directly between supplier and customer. Sensors and IoT, devices that capture voltage and current data to optimize charging and detect anomalies. Energy storage, large-scale batteries that store surpluses, especially from renewable sources, to release them at peak demand. Control systems, SCADA, advanced software that automates decision-making and grid balancing. The architecture of a smart grid is generally divided into layers: perception, network, and application. Home energy management, HEM, schemes, emphasizing their critical role in the smart grid's consumption side. Its primary goal is to make electricity consumption smarter and more efficient through systematic coordination of appliances and local distributed energy resources, DER. The essential devices of a smart home are introduced, including the most well-known brands, so they have become commodities in the smart home device market. A smart home is equipped with devices connected to the Internet, IoT, which allow automation and remote control of functions such as lighting, security and air conditioning. With the aim of improving comfort and energy efficiency, the smart home needs a stable Wi-Fi connection and a control center, a hub or virtual assistant, to manage the devices. The main devices are voice assistants and smart displays act as the brain of the system, allowing control of other devices through voice commands and touch interfaces. Smart lighting allows you to control the on, off, brightness and color of the lights remotely, which contributes to energy savings and the creation of personalized environments. Smart plugs and power strips turn common appliances into smart devices, allowing them to be remotely controlled, programmed, and monitored for energy consumption. Smart security systems offer real-time monitoring, motion detection, and remote access to increase home protection. They include cameras, door and window sensors, video doorbells, and locks. Smart thermostats optimize home heating and cooling by learning the user's habits and automatically adjusting the temperature, which translates into energy and cost savings. Home energy management, HEM, schemes, emphasizing their critical role in the smart grid's consumption side. Its primary goal is to make electricity consumption smarter and more efficient through systematic coordination of appliances and local distributed energy resources, DER. The main benefits are reduced electricity bills, decreased peak demand, and decreased peak average ratio, PAR. Pricing schemes are based on the analysis of tariff models such as real-time price, RTP, time of use, TOW, slanted block rates, IBR, and critical peak price, CPP. HEM schemes are categorizing into two types, communication-based and optimization-based. The diagram shows the distribution of the equipment in a HEM system. Optimal scheduling of smart home appliances using mixed integer linear programming. A simple MIP and refined math heuristics framework is addressed, where a greedy heuristic is used to trigger a general-purpose MIP refinement procedure. Moreover, a more sophisticated heuristic is presented. Computational results on a smart grid energy management problem are presented, showing that the method and the heuristic produce sound results. The approach is based on two ingredients, an initial heuristic, and a MIP model. The heuristic needs not to be very effective, as its role is just to initialize a pool of feasible solutions. The more diversified the better. The MIP model itself needs not to be very sophisticated, as it is automatically resized by the general-purpose MIP refinement procedure. Nevertheless, the combination of the two can be much more effective than the sum of its parts, in the sense that the two modules work in a highly synergic way and can produce outcomes whose solution quality can only be matched by sophisticated ad hoc heuristics. The battery-pumped heuristic, even obtaining good results, cannot achieve the effectiveness of the new approach but is much more complicated than the standalone heuristic. The case of study considered a time horizon of 24 hours, subdivided in 96 time slots of 15 minutes each. Experiments were grouped into 4 sets according to 2 main parameters. The first parameter is the flexibility of the user time preference constraint. We considered 2 levels of flexibility, namely high flexibility, HF, meaning that the appliance can be scheduled at any time during the day, and medium flexibility, MF, meaning that appliances can run inside a 12-hour randomly generated time window within the day. The second parameter is electricity cost. It can vary either every 2 hours, BC, or every time slot, TC. For each of the 4 resulting sets, namely HFBC, HFTC, MFBC, and MFTC, were considered 10, 20, or 30 appliances, respectively, and solved 5 random instances for each of the 12 combinations, 60 instances in total. 7 solution approaches were compared. Greedy alone, our standalone greedy algorithm without multi-start enhancement. Greedy, our greedy algorithm applied n times by starting from the n possible shifts of the initial priority vector, taking the best solution found and storing the others. Battery, our battery algorithm applied after greedy alone. Greedy plus battery, our battery algorithm applied after greedy. Plex, the state-of-the-art IBM Alog Plex MIP solver used as a black box, with its default setting, stopped as soon as the first feasible solution is found. Plex plus polish, Plex's polishing refining heuristic applied right after the root node and for a total of 10 nodes, when starting from the feasible solution found by the previous Plex algorithm. Greedy plus polish, our proposed MIP and refined scheme, such as the previous Plex plus polish algorithm but starting from the list of all feasible solutions found by greedy. The MIP model. The appliance model operations are a set of sequential phases of uninterruptible power, each of which uses a given total amount of electrical energy. For example, the typical phases of a washing machine are pre-washing, washing, rinsing, and spinning. The set of phases is also called the power profile of the appliance. Depending on the appliance, the duration of the phase may vary, as long as the delay between phases. For example, the spin of the washing machine should begin within 10 minutes of finishing rinsing. The total energy given for a phase may be evenly distributed over time, or it may vary. The MIP model represents the latter case with per-phase limits on instantaneous energy consumption and includes 3 classes of energy sources: power grid, domestic renewable energy, and energy storages. The power grid announces the maximum amount of energy available, the maximum power, for each instant. This maximum power may be different from the actual maximum power of the user's contract. In fact, a common feature in the smart grid paradigm is that maximum power is broadcasted dynamically according to the state of the grid, so that users adjust their demands and thus prevent dangerous power outages. Along with maximum power, the cost of energy also changes over time. Renewable energy sources could provide free energy, but with limited availability. For example, the performance of a PV plant depends on geographical position, weather conditions, and weather. The smart grid makes it possible to store energy when the price is low and use it more when the price of energy is higher. This feature represents a significant degree of freedom in terms of optimization. With the binary variables xki, skj and tkj, the model assigns a time interval k for the phase j of appliance I. The meaning of 1 for binary variables is xki, if in period k, the phase j of appliance I is assigned sik, if phase j starts just after the last period k, and TKJ, if is an interphase delay between phase J, 1 and J during the period K. The figure illustrates the meaning of the above variables in a simple case of an appliance with two phases. The first phase is assigned between hours 2 and 6, and the second between hours 14 and 16, dividing the day into 12 time slots. In this text, period is used in exchange for time slot. The main smart home restrictions of the model are presented below and ensure phase energy, that the energy allocated during the phases of an appliance meets the total given phase energy. Energy bounds, that the energy allocated in the phases that an appliance performs during any period belongs to the permissible range. Power safety, that the total power allocated over a period does not exceed the maximum power limit. This constraint can also be used to model additional unscheduled power demands that reduce the available grid energy during a period. Energy phase duration, the lower and upper limit in the number periods assigned for the appliance phases. Uninterruptible phase, that all time intervals of the phases are assigned continuously, implying that when an energy phase begins, it must end uninterrupted. Sequential processing, that the previous energy phase must be completed before a new one begins. Interphase delay duration, that the minimum and maximum periods between consecutive phases are met. Other restrictions that must be met are user time preferences, battery usage, battery charge, or discharge, rate bounds, battery energy functions, battery capacity bounds, and balancing constraint. The tests considered a time horizon of 24 hours, subdivided into 96 slots of 15 minutes each. The experiments were grouped into 4 sets according to 2 main parameters. Flexibility of the user's time preference restriction, 2 levels are considered. High flexibility, HF, which means that the apparatus can be programmed at any time of the day, and medium flexibility, MF, which means that appliances can operate within a randomly generated time window of 12 hours within the day. Electricity cost, it can vary every 2 hours, BC, or in each time slot, TC. The combination of parameters produces 4 sets, HFBC, HFTC, MFBC and MFTC, for each 10, 20 or 30 appliances are considered, and 5 random instances, 12 combinations, 60 cases in total were solved. In the results, each color represents a different appliance. The figure shows an example of 10 appliances scheduling on HFBC using greedy alone. Figure shows an example of 20 appliances scheduling on HFBC using greedy alone. Figure shows an example of 30 appliances scheduling on HFBC using greedy alone. The comparison of the 3 cases is presented. The position of the appliances is much more important in the case where the total energies involved are similar. In the first case, all appliances are assigned within the photovoltaic production area, while in the third case it is used almost exclusively in some appliances, and the rest is assigned to other time slots where saving becomes difficult, reducing efficiency. In the second case, the situation is intermediate. The columns of the table shows percent incur, the percentage cost increase with respect to the greedy alone algorithm. Percent STD, gives the percentage standard deviation of cost increase, and time, computing time in CPU sec. Superscript K means proven optimality for K out of 5 instances. The reported values are arithmetic means over 5 random instances. The table shows the statistics for greedy, battery, and G-ready plus battery approaches. The table shows the statistics for Plex, Plex plus polish, and G-ready plus polish approaches. The table shows the values of the objective function and time elapsed of the set 1 with high flexibility and by hour cost. The cases considered are Plex, Plex plus polish, and greedy plus polish. The figure shows an example of the greedy scheduling procedure of a single appliance composed of 2 phases, and user time preferences between periods 2 and 14. Thus, the total temporal complexity of the proposed greedy algorithm shows the importance of choosing the number of time slots to ensure a good compromise between calculation time and accuracy. The table shows the efficiency of the greedy and battery methods compared to greedy alone, measured in percentage improvement of CPU cost per second. The efficiency of the battery is quite better and improved the solution in a short time. The table shows the values of the objective function and time elapsed of the set 1 with high flexibility and by hour cost. The cases considered are Giretti alone, greedy, battery, and greedy plus battery. It is evident that, in terms of efficiency, the battery is quite better and can significantly improve the solution in a short time. The table shows a seemingly strange behavior. The efficiency of equipment with 20 appliances is always higher than that of one with 30. The reason should be sought in the characteristics of the photovoltaic source and the amount of energy it can provide. The figure shows an example of 30 appliances scheduling on HFBC using greedy plus battery, including the operation of energy storage. The figure shows an example 30 appliances scheduling and battery behavior on HFBC using greedy plus battery. The figure shows an example of 30 appliances scheduling and battery behavior on HFBC using greedy plus polish. That can benefit much more from a MIP mathematical complex model, perfectly adapting the power profile of household appliances in the area where there is photovoltaic energy, or where the cost of energy from the electricity grid is lower. The figure shows an example of 30 appliances scheduling and battery behavior on HFTC using greedy plus polish. The figure shows an example of 30 appliances scheduling and battery behavior on MFBC using greedy plus polish. The figure shows an example of 30 appliances scheduling and battery behavior on MFTC using greedy plus battery. The figure shows an example of 30 appliances scheduling and battery behavior on MFTC using greedy plus polish. Optimal scheduling of smart homes energy consumption with microgrid. Today, electricity distribution through smart grids is integrated and intelligent, including advanced digital meters, distribution automation, communication systems, and dispersed energy resources. Desired functionalities in smart grids include self-healing and optimizing asset utilization, and minimization of operating and maintenance expenses. Microgrids are considered to enable the widespread inclusion of renewable resources, distributed storage, and demand response programs in distribution. The Smart Home Energy Consumption Planning Problem is formulated as an integer linear programming model, MIP. Daily power consumption tasks are scheduled based on their operating window, earliest start time, and latest end time, and the goal is to minimize daily energy cost and decrease peak consumption. Modeling assumes that the smart building system has its own microgrid and decentralized resources, such as a wind generator, CHP generator, boiler, thermal storage and electrical storage. In addition, there is a connection to the electricity grid to obtain electricity during peak hours, or to sell electricity when there is surplus electricity generation. The model only provides the optimal schedule for a day, equipment capacity selection is not considered, and capabilities are provided. The electricity price profile can vary depending on the time of day. The model assumes that the weather forecast can provide 24-hour wind speed data. The list of notations used in the MILP model is given in the text. The constraints of the model are: capacity constraints. The input and output of each equipment must not exceed its design capacity. This covers CHP generator, boiler, electrical storage, and thermal storage. Energy storage limitations. It corresponds to the set of equations for managing inventory and energy storages. Wind generator output. The electricity production of wind generators must be calculated from the wind power generation equation. Energy balances. The electricity consumed during each period is supplied by wind generators, CHP generators, electricity received by electrical storage, minus electricity sent to electrical storage and the grid. The objective function is to minimize the total daily electricity cost, which includes operation and maintenance cost of the CHP generator, wind generator, electrical storage and thermal storage, cost of electricity purchased from the grid, and revenue from electricity sold to the grid. Wind turbines are a very important renewable energy in smart grids. Wind energy uses the kinetic energy of the wind and is a consequence of the difference in existing pressures, which causes the movement of air masses from high to low pressure. The generation of electrical energy from wind energy depends on the density, speed, direction and frequency of the winds, all random variables. The behavior of industrial wind turbines depends on their type. This differential modeling must be carried out from the synthetic hydroclimatic series that must implicitly represent the availability of effective wind for generation. Wind turbines generate energy if the wind speed exceeds 5 meters per second, and after 15 meters they change their behavior. Below 5 meters per second, there is no force to start the turbine. Exceeding 15 meters per second lose efficiency. Depending on the type of wind turbine, it does not increase generation, or unit wind consumption is increased. In the case study, compared to the case where tasks start at the earliest possible time, the peak of electricity consumption decreased from 290 kilowatts to 165 kilowatts, and the pattern of electricity consumption became flatter. The case study for a winter day could provide 18.7% savings compared with the earliest starting time case. The tasks can be scheduled to coincide with the cheapest electricity price while keeping their operation within the desired time window. The power output from the wind generator is not constant and varies from hour to hour according to the weather conditions and other constraints. But when a weather forecast can be used to predict the power output during the next 24 hours, or even longer, the domestic tasks can be scheduled to use the output of the wind generators when it is available, providing further savings for the customers. The scheduling formulation also increases the asset utilization, such as in the case study, the CHP generator was used more efficiently and became the main supplier of electricity and heat. The case study has 30 homes with the following energy suppliers. CHP generator with a capacity of 40 kW, its electrical efficiency is 35%, heat to power ratio is 1.3, and natural gas cost is $2.70 per kilowatt hour. Wind farm with a capacity of 10 kW and a maintenance cost of $0.5/k. Boiler with capacity of 85 kWth and natural gas cost is $2.70 per kilowatt hour, and electrical storage unit with a capacity of 10 kW, the charge-discharge efficiency is 95%, these limits are both 10 kW, and the maintenance cost is $0.5/k. Thermal storage unit with a capacity of 20 kWth, the charge/discharge efficiency is 98%, discharge limit and charge limit are both 20 kWth, and the maintenance cost is $0.1/k. WHTH. A grid connection allows import and export of electricity. On importation, the price of electricity varies at different times, and it is paid to the market operator, and if the electricity is sold, the buyer pays $1/k. Each time slot lasts half an hour. The total heat demand profile is generated for a building with floor area of 2,500 square meters. For the electricity demand, each home has 12 basic tasks that consume electricity. These tasks are available to be scheduled according to the given earliest starting time, latest finishing time, their respective processing times and power requirements. There are 10 identical wind generators, with an efficiency of 47%, whose blade diameter is 1.6 meters and the wind speed is generated from a Weibull distribution with a mean velocity of 7 meters per second. The cut-in and cut-out wind speeds are respectively 5 meters per second and 25 meters per second, and the nominal wind speed is 12 meters per second. The wind generators do not produce any power when the wind speed is under the cut-in speed or above the cut-out speed. When the wind speed is above the nominal wind speed, the power output is at the maximum output, which is equal to the output produced at the nominal wind speed. Between cut-in and nominal wind speed, the wind generator power output varies according to the math equations. The figure shows the electricity rate per hour. In terms of electricity demand, each household has 12 basic tasks that consume electricity, as shown in the table. These tasks can be scheduled based on the earliest start time, the latest end time, processing times, and power requirements. When a time slot is allowed, household task and equipment uptime are scheduled to minimize the total cost of electricity. Tasks, such as interior lighting and fridge, have fixed electricity consumption period and have no other alternatives. But tasks with flexible operation time can be scattered as much as possible to avoid electricity consumption peak and utilize electricity generated from local generators as much as possible. But when electricity is cheaper from grid, it will be imported instead of generating from generators. Tasks have a constant consumption of energy during processing time, but this is not always realistic. For example, washing machines have different energy consumptions depending on the condition. Modern planning models consider tasks with variable energy consumption over time. The optimal heat balance, with the earliest starting time, is shown in the figure. Equipment operation time is scheduled accordingly to minimize the total operation cost. Electrical storage is used to make more efficient use of the wind generator's output. No surplus electricity is sold to the power grid. The optimal electricity balance, with time window, is shown in the figure. During this period, approximately 51% of the total electricity is imported from the electricity grid. The optimal heat balance, with a time window, shows that CHP provides heat more stably than in the earliest starting time case. The optimal electricity balance, with the earliest starting time, is shown in the figure. There are only two peak periods, early morning and afternoon. The other periods have a fixed electricity consumption. Only 30% of the total electricity is purchased from the power grid, with electricity being supplied mainly by local distributed resources, and no electricity is sold back to the power grid. The total cost is 18.7% lower than in the first initial start case. Buildings Demand Response Optimization. The paper presents a method for optimizing the demand-side energy management system, SEMS, of a small-size electric power management system, SEMS, such as an industrial complex or a university campus. Demands can be met through the main grid and distributed stochastic energy resources, such as wind and solar sources. The goal is to maximize the utilization of the demand cluster, allowing to buy, store, and sell energy at the right times to adjust the hourly load level. The SEMS has the function of forecasting energy-related production and utilization units. The main objectives of SEMS are resource conservation, environmental protection and price savings, while users have permanent access to the energy they need. Given the demand ranges, and based on energy price information, the SEMS optimally decide the hourly energy consumption for each demand and sends the total energy consumption to the energy suppliers. To optimize SEMS, an optimization algorithm based on linear programming, LP, was implemented. The methodology provides the monitoring and control of the demand management system. It improves the performance of structural demand down to the level of distributed energy resources. The energy surcharge produced by photovoltaic and wind power plants is transferred to their regional electricity grid. Energy consumption is determined by the LP method on all bus bars, and demand is met by the implementation of a protection system for photovoltaic and wind power plants. Excess energy from distributed energy resources can be stored in the battery and used by the load when there is a demand for energy. The energy management system improves efficiency and minimizes losses. The wind and solar system is a realistic energy supply which make high quality use the resources. The block diagram of SEMS is shown in the figure. This method can not only supply an agreement of low cost and high reliability for a quantity of area where energy conduction is not suitable, such as limit resistance, and install a new area which resolution the emergency of energy sources and environment pollution. Currently it is complex to use separately solar and wind energy circulating in the climate system. This is due to the desynchronization of hours and areas. The main components of the smart grid are local renewable energy system, including energy storage, local electricity system, regional power grid, and loads located on the smart grid. 13 points of demand are considered. The case study was realized at KS Rangasamy College of Technology, that is in a scenic campus area near Tiruchengoda, Tamil Nadu, India. Case study, IEEE 14 bus system located on the campus of KS Rangasamy College of Technology, KSRCT. The figure shows the KSRCT network, where you can see the location of the demand points, renewable sources, solar and wind energy, energy storage, and connection to the regional electricity grid. The table shows the KSRCT demand data. The scheduled demand is for 13 academic buildings during certain times of the day. The figure shows the maximum power consumption in KSRCT, consisting of the total connected load and the total power consumed. The results shows that the cluster of demands of energy management system using SIMS model increasing the efficiency and minimizing the losses. The overload energy produced by photovoltaic and wind power plants is transferred to the regional power grid. The energy consumption of the IEEE 14 system is determined by the LP method in all bars, and the demand has been met with the implementation of a protection system for photovoltaic and wind power plants. Remember, all science as it grows toward perfection becomes mathematical in its ideas. Alfred Whitehead. Thank you very much for your attention.